all, if you go to today's date under the website, you'll see that we've got another check-in that'll be due tomorrow. It's going to be a follow-up on the one from last time that was about confidence intervals, and it also has a question about hypothesis testing, which we covered a little bit last week, and we're going to cover in more depth today. So the big thing that I'm hoping that you will put in your answer when asked about what a 95% confidence interval is, I've asked you to describe what that 95% means, and what I'm looking for there is that you describe the 95 refers to the proportion of intervals. If you were to do the same sampling many, many times, the proportion of intervals calculated that includes the true parameter of interest. And so what it specifically is not is the probability that the truth is in that specific interval. So make sure that you do not say it's the probability that the truth is between 0.1 and 0.5 or whatever the interval is. The 95 refers to basically the sampling space. So if you were to sample the same data points many, many times, so if you were to kind of, like we did with the Magnolia data, where you all each generated a sample of 30, and you each calculated a confidence interval, and when we did it using the actual truly random sampling that I had sort of artificially created via that little application, you saw that 95% of the intervals, so each of you got a different interval, but about 95% of them contained the true value and 5% didn't. So the 95 refers to the proportion of intervals with an S that would contain the truth if you were to do the process many times. So hopefully you'll say something like that in your answer. All right, so we're going to start by doing some on hypothesis testing, and then we will follow up with some partitioning variability. One other thing, if you attended the extra credit yesterday, there's like a little spot on Canvas where you can input a little, like 1 or 2 sentences about what you learned at the seminar. So thank you for those of you that came. Hopefully you found it useful. We'll have 3 more seminars this semester, so there will be other opportunities if you weren't able to come to the last one. Okay, hypothesis testing and p-values. So what I want you to do is go ahead and copy this template that I've created here into RStudio Pro. So you'll pull that in via the version control process that we've been using. And then I want you to go back to that little Magnolia data app and collect 30 data points, which basically just means clicking that picture of Magnolia 30 times and then pulling the code on the right side of the application into R. Or if you would rather, you can also use the data that you generated on Thursday. You could copy that code into your new Cordo or QMD document if you would prefer. So either way is fine. Just make sure you get 30 data points. Bring the data into R and fit a linear model predicting leaf length from leaf width. And then see if you can determine your coefficient for beta hat 1, what the t statistic is, what the p-value is, and then think about what hypothesis this p-value is assessing, and then we will talk about it together. Oh, and one other thing I wanted to mention, on the website, you'll notice the schedule. You may have noticed this last week, but the schedule shifted a bit. I moved our midterm back to the 11th. And that's mostly so that we can make sure you still have time for a review. I want to make sure that we have a little bit of time for that, particularly because the midterm, sometimes the exams, especially for a class like this, or a lot of the in-class time is spent on the applied stuff like working in R, and the midterm sometimes can be a little different because it's a little bit more of the thinking through the mathematical side of it, and I want to make sure that everyone has a good chance to kind of have some practice on that type of assessment before we do it. So it'll now be on the 11th. It's going to be on Canvas. The midterm will be, and I'll give you more details kind of that as we get a little bit closer. But all right, so go ahead and get this data into R. Calculate that beta hat 1 coefficient, the t statistic, and the p-value. Okay, I'm going to go collect some data here. All right. I'm randomly sampling 30 leaves to get their length and their width. And then I will pull it into this little R, or the QMD file. Here, let me delete what I had done in the last class so we can start fresh here. All right, so I've got 30 observations. If I want to fit a linear model to predict the leaf length from the leaf width, what would I do for that? Yeah, LM. The length to be my outcome and the width to be my predictor. Leaf length, the leaf width. Yeah, in this case it's magnolia data, yeah. Yeah, great. And if I wanted to save this, oh, this is like a weird one. Cool. If I wanted to save this, what would I save the output as? Yeah, I could save it as something like mod. And so I end up with this output here that I can, if I wanted to get the beta hat 1, what can I do to see what that is? Yeah, I can look at the summary of my model. And so in my case, what is my beta hat 1 value? Yeah, it's 0.064. And so what does that mean in the context of this model? Exactly. So for every centimeter increase in leaf width, we'd expect a 0.64 increase in leaf length. Great. And let's see, what else did I request? Oh, the t. What's the t value in my case? Or the t statistic? Yeah, it's this 0.216. If I didn't have this column of data in my output, if I only had the estimate and the standard error, how could I calculate the t statistics? Exactly. So if I take my beta 1 hat, so this 0.06463, and I divide by my standard error, I get my t value here. So this is something that could end up on an exam, for example, where maybe I would leave out parts of this table and you would have to use other parts of the table to calculate it. So if you had the t value, you could get to, well, you would need 2 of these to get any one other. So like, let's say I had the t value and the estimate. I could get to the standard error because I know that the standard error is equal to the estimate over the t value. Or if I had the estimate and the standard error, I know I could get to the t value because I know that's equal to the estimate divided by the standard error, etc. So these are all, I could get to kind of any one from the other 2. Great. And what's my p-value for this t statistic? What is it? 831. Yes, 0.831. And what does that mean in the context of this model? What hypothesis is that p-value testing? Yes?
That the real leaf width slope value is 0?
exactly, that the real leaf width slope value is 0, or that there's no relationship between the width of a leaf and the length of a leaf. And what does this probability represent? Like, what is this 80%, 83% probability telling me? Yes, exactly. I failed to reject the null hypothesis. And it's the probability of seeing a t-statistic as extreme or more extreme than what I've observed, given the null hypothesis is true. So given the true t-value is 0, what's the probability that I would see a 0.216 or more extreme if the truth was really that it was 0? And that probability is 83%. Now this is interesting because I know, because I generated this data, I created the application that this data came from. I know that there is really a relationship between leaf length and leaf width, and it turns out in this particular sample I just wasn't observing it. My guess is that most of you got larger numbers for this estimate. What do you think? Let's check my confidence interval. If I wanted to get my confidence interval, what would I do? Conf int. Exactly. And I ended up with negative 0.54 to 0.67. And so even though this confidence interval does include the null, it actually also includes the truth. The true value for the relationship between leaf length and leaf width was something like 0.55. And so statistics are still working as we would expect it to here. Although, as we learned last class, with all of us doing it, so if everyone in this class were to pull 30 observations from that application that I created, we would expect about, on average, one person to have a confidence interval that doesn't contain the truth based on what a 95% confidence interval means. All right, so I'm going to just show you, I'm going to kind of, with pictures, sort of show a little more about what we're talking about when we're talking about hypothesis testing and what I mean by testing under the null, or under the null being true. So, in the context of regression, or in this case, simple linear regression with just one variable, our null hypothesis is that the slope, or the true beta 1, is equal to 0. Our alternative hypothesis is that it's not equal to 0. And importantly, that means it could be bigger than 0 or smaller than 0. So these are two-sided hypothesis tests. We're kind of agnostic as to whether the slope is positive or negative. We're just testing whether it's something different from 0, whether there's some relationship between x and y. So the whole premise here is that we're looking at this probability under the null hypothesis. And so to do that, we can generate what we would expect to see under the null hypothesis, and then compare what we saw to that. And so it turns out under the null, so the null being that beta 1 is equal to 0, the t-statistic, which again is that beta hat 1 over the standard error of beta hat 1, this has a t-distribution with n minus 2 degrees of freedom. And so what I've generated here is, I've generated something from a t-distribution with n minus 2 degrees of freedom. You can see kind of how that would look. It's centered at 0. This is under the null. So this is assuming that the null is 0, or the t-statistic is 0. And this is basically the distribution of values you would expect to see. So what I mean by that is, if I had made my little application, so we know that the true beta 1 in the application that you all pulled from was like 0.55. If I had made another one where there was no relationship, where the truth was 0, and we each calculated a t-statistic, so under the null, if we each calculate our t-statistic, we would expect, if we were to kind of plot all of those in a histogram, we'd expect them to look something like this, where the majority of us would get t-statistics right around 0. A couple people might get them kind of down at this, like between negative 2.5 and 2.5, and we wouldn't really expect to see many more out here. So this is like the distribution that you would see if the null was true. So if truly there was no effect, if beta 1 was 0. Okay, so I did this again. I in the slides, I pulled a different sample of leaf length and leaf width data using the app. This time I had a larger sample size. I have 98 degrees of freedom, meaning that I pulled from 100. I pulled 100 observations, so I clicked on that little picture 100 times. What t statistic did I observe for my beta hat 1 here in this output? Yeah, this 2.826. And again, how could I get that 2.826 if I only had these first two columns? Exactly, I could take this estimate and I could divide it by the standard error, and that would give me this 2.826. Great. So I can draw that on this distribution of the t statistic under the null hypothesis. So here I've drawn the observed test statistic. This is that 2.826, so this is like that 2.8. And I've also drawn the inverse of it, this basically negative 2.8. And that's because, again, this is like a two-sided test that we're doing. So we're basically seeing if you're more extreme, and more extreme means farther from 0, so farther from the null. So there's two ways you could be more extreme. You could be kind of up here in this space, so this would be bigger values than 2.826, or you could be way down here with smaller values than negative 2.826. So how can we compare these statistics to the distribution under the null? Well, we could quantify how much mass of this distribution falls in these extreme values. And that's exactly what the p-value is doing. It's quantifying what proportion of the values in this distribution are on either the right or the left side of these observed statistics. So the p-value is the probability of observing a statistic as extreme or more extreme than the observed test statistic given the null hypothesis is true. And so on this same distribution, I can basically have highlighted the area over here on the right and over here on the left that are more extreme than what I've observed. So as extreme or more extreme than the observed test statistic. If I wanted to calculate the proportion of area greater than 2.826, so basically this area over here, I can use this pt function where p is going to tell me the probability, and t is saying that I want it to be under the t distribution. And the first argument of that is going to be the observed statistic, so in this case 2.826. The degrees of freedom is 98 because that's the degrees of freedom in my model. That's n minus 2. I had 100 observations, so n minus 2 is 98. Lower tail equals false is because I don't want the lower part of the distribution. I want this upper part up here. And I end up with 0.00285. So this tells me that the proportion of the area greater than 2.826 is 0.00285. If I want the proportion of the area less than negative 2.826, so I want this area to the left over here, I can use that same pt function. I'm going to use negative 2.826 as the quantile I'm interested in. Degrees of freedom is still 98. Why don't I have lower tail equals false here? Because it's true, right? Because I'm interested in basically I am interested in the lower tail this time. I'm interested in the area on the left. And so how do you think I could get if I want to sum up all of this red area, so I want both of these, what do you think I would do to do that? Yeah, I could do times 2, or just add, I could add these two pieces together here. So I could add up the first piece of code that got me the upper tail, and I could add up the second piece of code which got me the lower tail. And because this is a symmetric distribution, as you said, I could also just do times 2. So I could take the observed test statistic with my degrees of freedom. If I'm using a positive test statistic, I'll set the lower tail equal to false, and I'll multiply by 2. And so I get this p-value, 0.005712, which if we go back to my very first example, that's exactly what we saw. All right. Are there any questions about that hypothesis testing or anything? What a p-value means? the important part that I think is most often forgotten about p-values is this: given the null hypothesis is true. So when you're taking your little check-in, make sure that you say that. That's an important piece because the test is under the assumption of the null hypothesis. The other thing that people sometimes make the mistake on is they'll say it's the probability of observing a test statistic, which it's not the probability of that exact statistic. It's of that statistic or more extreme. And that's also important because for these continuous distributions, the probability of seeing an exact single value is actually 0. So you want to add up all the mass, not just the single value. All right, great. Moving on to partitioning variability. This part, I think, is very fun. This is one of my favorite parts of this class because I think it's one of these parts where it's like pretty easy math. It's just like basic algebra, adding a couple things together. But it kind of all, for me anyways, makes it click what we're doing with our models and how we can sort of make some sense of how well our model fits our data. And so what we're going to be demonstrating today is that you can show that the total variation in the response y, so the total variability of the thing that you're trying to predict, the variability in this case, like in the case that we just did with the magnolia data, the variability in your leaf length is going to be equal to the amount of variation that's explained by your model plus the unexplained variation in the residuals. And so perhaps that makes sense if you just sort of think about what your model's doing and what the residuals are, that if you sum up those two things, you'll get the total variation in y. But this has some nice properties because it allows us to do things like, for example, you could look at the proportion of the average variation explained by the model to the average variation in your residuals. You could look at kind of the relationship between those to help assess how well your model fits your data. So basically, proportional to how much variation is left over to still be explained, does your model kind of improve does it improve what you're estimating here? So here I have pulled again some leaf length data, and this is my distribution of my y variable, leaf length. And so what I'm saying here is this variation. Here I've drawn like one standard deviation on either side. Basically the variability just describes how wide this distribution is. And this partition variability is saying that we can show that the variation in this y variable is equal to the variation that I'm able to explain by my model. So in my case, my variation I'm able to explain by the leaf width plus the amount that I'm not able to explain. So the way that we're going to describe the variation in the response y is we'll start with this sum of squares total, which is equal to the sum of y minus y bar. Y bar is just the average y value squared. And so if I'm doing this in R here, I can use the summarize function along with the sum. What would I plug in for this first part if if my outcome is leaf length? Yes, it would be leaf length, yes. And then what about for the second part here? What would I plug in for this? Exactly, the mean of leaf length. And then I could square that whole quantity. So if I do that, if I take the sum of leaf length minus the mean of leaf length squared and sum all of those up, I end up with this sum of squared total of 3008. Just to sort of show you how this is related to the total, to the variability or the variance of leaf length, this sum of squared total is equal to the variance of leaf length times n minus 1. So if I divide this by n minus 1, I would get the variance of y. So this is just the equation of the variance of y, so the sum of squared total is the numerator of that. So if I take the variance of leaf length times n minus 1, I get that same sum of squared total. This is just to show you how this is related to maybe quantities you've seen in previous classes. Okay, if I'm interested in the unexplained variation from the residuals, this is the sum of, I'm going to use the sum of squared errors. And we've seen this already in this class. We've used this for a couple things. This sum of squared errors is just the sum of the residuals. So the sum of y minus y hat squared. And so if I wanted to calculate that, what would I plug in for this first part of my equation? Leaf length, exactly. And what about for the second part? What function can I use to get y hat from this model? Fitted, yes, exactly. I can use fitted mod to get the y hat values. And so to get the sum of squared error, I can sum up leaf length minus fitted mod squared. And this will give me the sum of squared errors of 2,781. Does anyone know another function I could replace this inside if I want to just use a single function instead of doing y minus y hat? Yes, residuals, exactly. So that this inside part here is just equal to the residuals. And so I can use the residuals function, and that will give me the exact same answer here, 2781. Just to show you how this is related to something else we saw, last class we talked about this sigma, that average variation in the residuals. And so that value is going to be equal. So that sigma, the sum of squared error is equal to the sigma squared times n minus 2. And that's because this sum of squared error divided by n minus 2 is equal to sigma hat squared of the errors. So you can use this function. This is not necessarily how I would ever calculate this, but just to show you the relationship between things we've already seen in this class and this sum of squared error equation. All right, and then finally we have the variation explained by the model. And so for that we have the sum of squares model. And that's equal to the sum of y hat, the fitted y values, minus y bar, the average y values squared. And so if I'm using this function to calculate that, what would I put into this first part? Fitted, exactly, fitted of that mod function. And what about for this second part? What is it? Mean, yes, exactly, mean of leaf length. So I can do fitted mod minus mean of leaf length, that whole quantity squared. And that gives me the sum of squared model, which is 227. So just putting it all together into one summarized function, I can look at the sum of squared total, the sum of squared model, and the sum of squared error. Now, based on what I had told you right at the beginning of class, if I added up the sum of squared model and the sum of squared error, what do you think I would get?
Sum of squared total.
Yeah, the sum of squared total, exactly. So if I do this, I end up with 3008, which is exactly the same as what I got in my sum of squared total. And what about if I subtract the sum of squared model from the sum of squared total? What would that be? Sum of squared error, exactly. So just sort of to show that all three of these quantities, if you knew any two, you could calculate the third. So if I take the sum of squared total minus the sum of squared model, I end up with the sum of squared error. And similarly, if I take the sum of squared total and subtract the sum of squared error, what would I get? The sum of squared model, exactly, that 227. Great. All right, so building on that, there's this concept of degrees of freedom, which we've sort of briefly touched on a little bit. But a sort of high-level summary of what this quantity summarizes is It's going to be the number of observations used to estimate a statistic minus the number of things that you're estimating. So for example, with the sum of squared total, how many observations do I have here in this particular example? N, exactly. So I've got N observations in this data set that I'm summing over. And how many things in this equation are estimated? So what would this, is this y, what does this represent? Like in the leaf length example, what would that be? Or in the magnolia data example, I guess. Leaf length, yeah. So would that be estimated or observed? Observed. And how many of those would I have? N, yeah, so 30 in my case, and N if I in this sort of general example. Okay, so those are observed things. We have N observed things. And then what about this? This is the y bar, which is this an estimate? Yes. And how many different y bar values would you have for a single data set? Well, you'd only have one because it'd be the same for all of them, because everyone would have the same, all 30 of them would have the same estimate for the mean. And so you have one thing that's being estimated. Basically, you've got the same mean for all of your observations. Each of these, if we were to write out, let's say we had 3 observations and they were like 4, 2, and 1. If I were to write out what I was estimating here, I would take 4 minus, what is the mean of this? This is 7 divided by 3. I'm just going to write that as 7 over 3 here. So 4 minus 7 over 3, 2 minus 7 over 3, 1 minus 7 over 3. So basically we just have one thing that the y bar here is the same every time. So we're estimating one thing. We have N observations. The y bar is the one thing that we're estimating. So using this little rule of thumb that the degrees of freedom is going to be the number of observations minus the number of things we're estimating, how many degrees of freedom do you think the sum of squared total would have? N minus 1, exactly. And this also is why when you're estimating the variance of y, so if we were estimating the variance of y, that's going to be equal to the sum of squared total divided by the degrees of freedom, N minus 1. Okay, let's do the sum of squared error now. How many observations do we have here? Still N, exactly. And how is y hat estimated with simple linear regression? Like, what's the equation that we use if we've got one x variable? Mx plus b, yes, and sometimes we say like beta 0 plus beta 1 hat, but the same kind of idea. Yes, so we can estimate this as beta hat 0 plus beta hat 1x. And so from this, how many things are estimated here? How many parameters are we estimating? Two, yes, exactly, 2. So we're estimating the intercept and the slope. So how many degrees of freedom do you think we have? N minus 2, exactly. Great. if we had, so far we've only covered simple linear regression, where we've got one x variable, but pretty soon we're going to be covering regression where we have multiple x's, so like multiple variables that we're adjusting for. And so if we had something like this, where instead of estimating y hat using just beta 0 plus beta 1, beta hat 0 plus beta hat 1 x, what if we had something like this, where we have a second variable? So y hat is beta hat 0 plus beta hat 1 x1 plus beta hat 2 x2. Now, how many things do you think we're estimating in our model? 3, yes, exactly. And so what do you think the degrees of freedom would be for the sum of squared error if this was our model? N minus 3, exactly. And what if we were fitting a model like this, where we have, instead of just having 2 variables, we actually have 3 variables. So we've got beta hat 1, x1, beta hat 2, x2, and beta hat 3, x3. How many things are we estimating here? 4, exactly. So now the degrees of freedom would be n minus 4. So the way that this generalizes, people sometimes refer to the number of variables in your model as k. And they also sometimes refer to the number of parameters in your model as p. And so the sum of squared errors, the degrees of freedom for the error, or sometimes people call it the degrees of freedom for the residuals, is going to be equal to n minus k minus 1, or n minus p. So dependent, like k would be if there's 2 variables, k would be 2, so this would be like n minus 3. Or if you count the number of parameters, there's 3 parameters. All right. Great. So then we know that the sum of squared total is equal to the sum of squared model plus the sum of squared error. And it turns out, in the same way, the degrees of freedom for the sum of squared total is equal to the degrees of freedom of the sum of squared model plus the degrees of freedom of the sum of squared error. And so in the case of simple linear regression, we can plug in what we just calculated for each of those. So sum of squared total, the degrees of freedom is n minus 1. Sum of squared error, the degrees of freedom is n minus 2. And so using that information, I want you to spend a couple minutes thinking about or seeing if you can quickly derive how many degrees of freedom you think the sum of squared model would have. And then see if you can extend it to generalize to k. So if we had k variables that we were adjusting for, what the degrees of freedom for sum of squared model would be in that case. Okay, can anybody tell me what the degrees of freedom for sum of squared model would be? 1, yes, exactly. So we can just look at this equation. We could move the 2 over here, and that would cancel out one of these. So like we'd end up with just 1 over here, and then we can move the n over, and that would cancel the n. So we just end up with 1. What would it generalize to if we had k variables in our model? Just it would just be k. It'd be p minus 1 or k. So if k is the number of variables in your model, this is going to, instead of being n minus 2, this would be n minus k minus 1. And so the n minus 1s cancel out, and you end up with just k. Are there any questions about this? All right. Okay, so it turns out that these quantities are very useful because it allows us to compare, on average, what is the what's the mean squared error or the average squared error versus what is the mean squared model. So basically, on average, how much of our variability are we explaining by the model compared to how much is left over? The sum of squared error is describing basically what you haven't described from your model because it's like from the residuals, and the sum of squared model is describing what you have described by your model. And so if we divide these by the degrees of freedom, we can get the average or the mean squared error in the mean squared model. The pattern here is that both of these are divided by their degrees of freedom. Related to this, if I took the sum of squared total and divided by its degrees of freedom, what would I get? So if I have like the sum of y minus y bar squared over n minus 1, what is this estimating? The variance, yeah, this is the variance of y. So each of these dividing by their degrees of freedom kind of gives us a quantity that's useful to us. If my model had three variables in it as opposed to one, what would this denominator be? N minus 4 if it had 3 variables, but 4 parameters, yeah. Yeah, and what would the denominator be for this one if I had 3 variables? It would be 3. So the degrees of freedom for the model is going to be equal to the number of variables in the model, and the degrees of freedom for the error is going to be equal to the number of observations minus the number of variables in the model minus 1. Okay, so the reason we're doing all of this is because it will allow us to basically compare this ratio, where the ratio is going to be the mean squared model divided by the mean squared error. And so what this tells us is basically how large is the amount of variability we're explaining from our model compared to the amount of variability that we're not explaining from our model. And so we can look at the distribution of what this F statistic would be under the null, and then compare this statistic that we've observed and get this probability, which is going to allow us to sort of to determine whether our model is significantly better than just an intercept-only model or a model that didn't include any variables in it. So under the null hypothesis, this is what an F distribution, or what this ratio would look like. Now, why is there nothing less than 0 here? Why can this ratio never be less than 0? Exactly. Both of the quantities here are squared, and so you can't have squared values that are less than 0. So this ratio is always going to be greater than 0, meaning that the F distribution is always going to be greater than 0. The F distribution, the F statistic under the null is going to look like this. And so you can see all of these statistics by using the ANOVA function from the LM output. So here I've saved my linear model as an object called mod, and then I use the ANOVA function, and ANOVA stands for analysis of variance. And it gives me this nice analysis of variance table, which includes the degrees of freedom, the sums of squared for the top line is the sums of squared is for the model. The bottom line, the one that says residuals, this is for the error. It gives me the mean squared model and the mean squared error. It gives me that F statistic, which is the ratio between the two, and the p-value, which is the probability of seeing an F statistic as extreme or more extreme than what we had given the null is true. So looking at this output, what is my sum of squared model here? Exactly, 226.7. And what's my mean squared model? Exactly, it's the same. And so for a simple linear regression, it's the mean squared model is always going to be the same as the sum of squared model because the degrees of freedom is 1. And what's my sum of squared error? Well, the mean squared divided by the f value would be the mean squared error. So that's, yeah, the mean squared model divided. But so that is true. The sum of squared error is going to be this, 2,781 value right here. But what you just said is true for the mean squared error. I could take my f value and divide by my mean squared error and get my mean squared error divided by my f value and get my mean squared error of 28. And what is the sum of squared total here? Exactly. It would be summing these two rows here. So it's something like 3007.9. And what about my F statistic? What's my F statistic? Yep, 7.9882, exactly. And is that F statistic statistically significant? Or is the p-value less than 0.05? Yes, so this is my p-value. And what does this represent? What probability is that? Given yes. So this is the probability that you would see a F value of 7.9882 or bigger given the null hypothesis is true. So the probability of getting a test statistic as extreme or more extreme than the observed test statistic given the null hypothesis is true. So this is that null hypothesis. And we're going to need degrees of freedom to be able to generate this null hypothesis, similar to how the T null was the distribution of that T statistic under the null was determined by the degrees of freedom. We're going to use the degrees of freedom here as well. So let's say my sample size was 100. What would my degrees of freedom of the sum of squared total be? 99, exactly. And what about of the sum of squared error? 98, right? So it'd be n minus 2. And what about for the model? 1, yep, exactly. And so I'm going to use these in just a second. To calculate the p-value under the t distribution, we used this pt function. What do you think we would use to calculate it under the f distribution? PF, yep, exactly. We're going to use the PF function. So P is going to stand for the probability, and F is for the distribution that we're using. And so the PF distribution takes 3 arguments, Q, df1 and df2, and so we'll come back to what these are based on those degrees of freedom that you just told me about. What do you think we would plug in for Q here? Exactly. We're going to plug in the observed statistic of 7.9882. And then df1 corresponds to the model degrees of freedom, and df2 corresponds to the degrees of freedom of the error, or of the residuals. And so I can plug all those in. I'll use the PF function. I'm going to plug in that 7.9882 for the Q value. df1 is 1, df2 is 98, and I end up with this 0.0057, which is the same as what the R output gave me for the ANOVA function. Why do I use the lower tail equals false argument? Yeah, because I basically, like, the F distribution looks something like this, and my statistic is maybe here, and I'm interested in this area over here, which is going to be on the upper tail rather than the lower tail. I'm trying to see basically the probability of it being greater than this value, so I'm going to use lower tail equals false. If I didn't have this, I could just use 1 minus the probability, and that would give me the same. If I took out the lower tail equals false, then I could use 1 minus PF, and that would give me the same thing. Because it would give me the area over here, and I know the total area is 1, because this is a probability distribution, and so. All right. So why am I not multiplying this value by 2 like we were doing with the p-value for the beta coefficient, which is t distributed? That's right, yeah. Because we only have one side as opposed to being a two-tailed test, or a two-sided test is just a one-sided test. And that's because it's not possible to have a negative F value because these are squared values, and so you can't end up with a value less than 0. So it's sort of hard to see because there's not a lot of mass on this side, but I've colored these to be blue just to indicate here the area to that is as extreme or more extreme than what we observed. So we observed an F statistic of 7.9882. There are not any negative values in the F distribution. The p-value calculates the values as extreme or more extreme, which in the t distribution, more extreme values are defined as farther from 0, so they can be either positive or negative. But in the F distribution, they have to be positive, and that's because we're looking at the ratio of two squared sums. So it's impossible if you square a value, it's always going to be positive. And so because of that, we're just doing this one-sided hypothesis test as opposed to a two-sided test. All right, so you can actually get these values from the summary function as well. So here, this is from the ANOVA output. This is that F value as well as the P value for the F value. When you use the summary function, down here at the bottom, you'll notice the F statistic, which is exactly the same. It also tells you the model degrees of freedom as well as the degrees of freedom for the error, along with the p-value. So the summary function will give you the pieces that match what the ANOVA function gives you as well. The other thing to notice here is that the p-value for the F test, this 0.005707, is exactly the same as the p-value for the t test for beta hat 1. And that's because in the unique case of simple linear regression where you just have one x variable, you just have one variable in your model, this is actually testing the exact same hypothesis. So this is always true for simple linear regression. It's not true for if you had more than one x variable. And the reason that is because the null hypothesis for an F test is that the fit of the intercept-only model, so a model that only has beta hat 0, and your model, a model that has beta hat 0 and beta hat 1, are equivalent. So your null is that these two equations are equivalent. The alternative is that the fit of the intercept-only model is significantly worse compared to your model. So if we look at this null, this is saying that basically this beta 0 equals beta 0 plus beta 1. And if this were to be true, that would be equivalent to saying that beta 1 is equal to 0, which is what the t-test is testing. So in the case where you only have one x variable, the f-test and the t-test are testing the same thing. When you have multiple x variables, it just adds them over on this side, so it'd be like beta 0 plus beta 1x plus beta 2x, that's equal to the intercept-only model, and so in that case, it's not the same as the t-test. It's not testing the exact same thing. So it's only in this case that where we're using simple linear regression, the f-test and the t-test are testing the same null hypothesis, that null hypothesis being that beta 1 is equal to 0. So when we only have one variable in our model, the p-values from the f and the t-test are going to be equivalent because you're testing the same hypothesis with those. The other thing to note here is the relationship between the f and t value. And so you'll notice the f value is 7.9882. The t value here is 2.826. And so it turns out the t statistic is exactly equal to, if you square the t statistic, you get the exact f statistic. And so the t statistic squared here is equal to this f statistic. And again, this is true in the simple linear regression case. It's not true once you have more variables in your model. But a squared t statistic is going to be f distributed. Are there any questions about that? All right, so let's spend a couple minutes. I want you to go back into your application exercise and use that Magnolia data to predict leaf length from leaf width, and then calculate the degrees of freedom for the sum of squared total, sum of squared model, sum of squared error, and then calculate the sum of squared total, sum of squared model, sum of squared error, and then calculate the f statistic for the model and the p-value, and determine what the null hypothesis is and the alternative hypothesis, and whether you reject the null given in your particular sample. For these two, I want you to see if you can calculate these by hand, by which I mean like using the summarize function and actually kind of calculating them from the equations. And then you can check your work using the ANOVA function. And the reason I think it's good to do that at least once is just to sort of solidify what these equations actually are, which will be useful for things like exams where you'll have to sort of be able to map these back to the actual equations. So try to see if you can do them by hand and then check and see if you get the right answer with the ANOVA function. So I'll give you 6 minutes to work on that, and then we'll do it together. right, let's start by calculating the total degrees of freedom. What would that be? N minus 1, exactly. And so there's this function. Within the summarized function, I can use the n function to calculate the number of rows. I can do n minus 1 to get the degrees of freedom total. And what about the degrees of freedom for the error or the residuals? What's that going to be in this case? N minus 2. And how about for the model? It's going to be, so we could use what we've already calculated. We could do df total minus df error because we know how these things are related to get it. We also could just say 1 because, yeah, it's 1. Very good. So now we can see what those are. So we end up with, in my case, I had taken 30 observations of this magnolia data, so my degrees of freedom total was 29, my degrees of freedom error was 28, and my degrees of freedom of the model was 1. If I want to calculate the sum of squared total, what is the equation for that? If leaf, the length of the leaf is my y variable here. The sum of leaf length minus, what was it? The mean of leaf length, exactly. And then that whole quantity squared within the sum. Yep, so that would be my sum of squared total. If I wanted my sum of squared errors, what would that be? The sum? The leaf length minus the, what did you say?
We just did residual mod squared.
Oh, residual. Yes, that works too. Yep, sum of the residuals mod squared. Yep, that will give me the sum of squared error. If I wanted to write it all out, what would be the same way to do it if I used like leaf length minus, what could I, to get the, if I was doing it without using the residuals function? Yeah, I could do leaf length minus fitted mod. These two are going to give me the same thing. And what about the sum of squared model? How would I calculate that? Yeah, so the sum of fitted mod minus mean of leaf length, that quantity squared. If I wanted the variance of leaf length, what could I use from what I've already calculated to get that? What describes the total variation in leaf length? Yeah, sum of squared total over degree of freedom total. And just to check that this gives me what I'm expecting, I'll make a leaf length 2, which is going to be the variance of leaf length, so we can check that those two things are the same. If I want the mean squared error, what would that be? Exactly, the sum of squared error divided by n minus 2, which is the sum of squared error divided by the degrees of freedom, the error. And what if I wanted the mean squared model? What would that be? Sum of squared model divided by df model, which is just the same as the sum of squared model because the degrees of freedom of the model is just 1 in this case. If I want the F statistic, what is that going to be? The mean squared model divided by the mean squared error. So it's the ratio of the variation described by the model divided by the variation that's not described by the model that's left over. Exactly. If I wanted to calculate a p-value for that F statistic, what function could I use? PF. And what would I put in for the first argument for Q? What would be my observed? Yeah, F, exactly. And then what would I put in for the first degrees of freedom? DF model. And then my second degrees of freedom would be DF error. Okay, let's see if this all works. There we go. All right, so if we run all that, we get a whole bunch of things. We've got our sum of squared total, which we know is equal to our sum of squared error plus our sum of squared model. Here, I'm just showing you that my sum of squared error, when I calculated it using the residuals function, was exactly the same as when I calculated it by hand by taking the y minus fitted of the model. So these two are the same as what we expect. I calculated the variance of the leaf length, which is equal to the sum of squared total divided by the degrees of freedom total, or n minus 1. Just as a check, I used the var function to calculate the variance of that, and these got exactly the same value, so my equation worked. The mean squared error is the sum of squared error divided by the degrees of freedom of the error. The mean squared model is equal to the mean squared model, or the sum of squared model divided by the degrees of freedom model. The F statistic is the ratio of the mean squared model to the mean squared error. And the p-value, oh, this is wrong. I left something out. What did I leave out of this p-value here? Yeah, the lower tail equals false. So I should, if I put that in, I end up with 0.8307. So if I look at ANOVA mod, I can compare what we got to what the ANOVA function tells us, and we end up with the same values here. I end up with that 0.8307 for my p-value, an f value of 0.0466, and my sum of squared and my mean squared error, etc. Now, one thing, we only have a couple minutes, but just to sort of help think about this, for this particular data set, I had 30 observations. If I had more observations, how do you think, if we're looking at this table, what would happen to the standard error as I increase the number of observations in my data set? So I can do this, I can go to my little application, and I can click on it like way more than 30 times. Like, let's say if I click on it like 100 times. How many have we done so far? 50s, 60s. Okay. So as I get more and more observations, my standard error is going to get smaller and smaller. And that's because the standard error has the square root of n in its calculation. The standard error is equal to the standard deviation divided by the square root of n. And so the sample size, as the sample size increases, my standard error is going to decrease. So if I run this, for example, now on this new data set, I ended up with a smaller standard error. And how does the smaller standard error impact your t-value? It makes it larger, exactly. So, what is it? Because you divide by the standard error. So what this means is, as my sample size gets bigger and bigger, even if my estimate stays exactly the same, my t-statistic is going to get bigger, making my p-value smaller. And this is why sometimes people don't like p-values, because they're functions of the sample size. And so what they do is, because you can detect, as your sample size increases, you can detect differences from 0 that are infinitesimally small. And so the p-value by itself doesn't tell you the estimate. It just tells you whether it's different from 0. And technically, 0.000001 is different from 0. And if you had a big enough sample size, you could have a significant p-value for essentially a meaningless estimate. And so it's one of the reasons why the p-value needs to always be interpreted in conjunction with an estimate itself. All right, thank you very much. I will see you all on Thursday.